Let us consider another example, this time the arctan function. One of the things that you may recall is that arctan has as its derivative 1 over 1 plus x squared. So we can integrate this to obtain arctan. You will notice also that 1 over 1 plus x squared can be represented as the geometric series of negative x squared, so that we can integrate the sum of negative x squared to the k, as k goes from 0 to infinity. Again, by rearranging terms, doing a little bit of work here, we see that we get the sum, k goes from 0 to infinity, of negative 1 to the k times the integral of x to the 2k, that is, x to the 2k plus 1 over 2k plus 1. We have to deal with the constant of integration, but again, since arctan of 0 equals 0, it is irrelevant. We therefore obtain the Taylor series x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, etc. Once again, no factorials in those denominators. And once again, it is important that x remain less than 1 in absolute value in order for this series to converge, because we used the geometric series as its basis. There is one last series that will be very helpful to us. This is the binomial series. It is the Taylor series for 1 plus x to the alpha, where alpha is a constant. This series is 1 plus alpha x plus 1 over 2 factorial times alpha minus 1 times x squared. Well, there are a lot of other terms here. Let me say simply that the kth order term is alpha choose k times x to the k, where by alpha choose k, I mean a binomial notation. This is the number alpha times alpha minus 1 times alpha minus 2 all the way down to alpha minus k plus 1. Take that product and divide by k factorial. For example, if alpha equals 2, then what does the binomial series give you? 1 plus alpha times x plus 1/2 alpha times alpha minus 1 times x squared. That simplifies to x squared. All other terms involve an alpha minus 2. Hence, the coefficients are 0. And we obtain, of course, what the Taylor series for this polynomial must be. When alpha equals negative 1, we're really looking at a variation of the geometric series for 1 over 1 plus x. This, however, holds for all values of alpha. For example, if we take alpha equal to 1/2, so that we're looking at the square root of 1 plus x, then one can evaluate these binomial coefficients and obtain a Taylor series for that. In this case, in particular, this is only going to remain valid for x less than 1 in absolute value. We now have a full collection of Taylor series. Many of these have domains of convergence that are infinite. E to the x, cosine and sine, and cosh and sinh. These are the nicest Taylor series that you're going to run into in this course. However, from this lesson, we have another collection of Taylor series that are guaranteed to converge only when x is less than 1 in absolute value. This is the geometric series, the series for log of 1 plus x, the series for arctan, and the binomial series. These, one has to be a bit careful with. but as long as you are within the domain of convergence. These are wonderful series.
The moral of this lesson is that so long as you are within the domain of convergence, you can do wonderful things. Check out the bonus material for this lecture for an additional example. In our next lesson, we'll consider what happens when you wish to focus your attention on some specific location, an expansion point.